Welcome to the 11th video in Introduction to Quantum Field Theory. This video is on the Euler-Lagrange equation in the context of field theory. So this is going to be a very, very short video, actually. I think the shortest of the series, maybe like 5 minutes or so. The idea is that in classical physics, so without considering field theory, so non-field theory classical physics, you have the Lagrangian, which is Q dependent upon Q and Q dot, where remember this is generalized, or these are generalized coordinates, and these are generalized velocities. So we talk about in classical physics, we talk about I'm going to say generalized, but coordinates and velocity. But in field theory, everything is probabilistic because you no longer have a specific knowledge of where things are. They lie continuously throughout a field. They're no longer at points. And so in field theory, we have something called, or we have Lagrangians, but they depend on the field, which actually depends upon position. And then instead of the derivative with respect to time, we have the derivative of the, or we have the just full gradient. So instead of only considering time, like in here, we consider the derivative with respect to every coordinate. And so instead of talking about coordinates and velocity, we talk about field, um, field and field uh, gradients. So field and field gradient configurations. So this looks at how the Lagrangian evolves with respect to position and velocity, but this looks at how the Lagrangian changes with respect to the field and how the field changes in space. So I don't know if that's a word, to appease the gods of special relativity, the Lagrangian density is introduced. So Lagrangian density to appease the special relativity gods. And this is typically written with a fancy L, and it depends on just the field and the change of the field, the gradient of the field. And it is defined such that the Lagrangian is equal to the integral over space of the Lagrangian density. And this implies that the action is equal to, it's still equal to the integral over time of the Lagrangian, but it's equal to the integral over space-time of the Lagrangian density. And you might be wondering, so what is the Euler-Lagrange equation? Well, you can see that this, even though now you're dealing with integral over spacetime, the equation looks remarkably similar to this one. So you can actually quite literally take the Euler-Lagrange equation and replace normal L with squiggly L, and Q with phi and with phi. Except these become the mu's like this. See that this is the Euler-Lagrange equation for field theory.